Technically, it's also live. 252. This is your midterm review. I am Miles. I'll be your instructor for the first two sections. So that's going to be Lab 1, Map Essentials, and Lab 2, Latitude and Longitudes. So if you're here in chat, please go ahead and say something now, just so we know that people are watching. Dexter, the other instructor, will let me know when someone has said something. We'll start when someone talks.
Tez said he's not even in this class.
Thank you, Tez. We can now start. So, GY 252 midterm review. Isn't this projector really cool? Nope, that didn't work. Oh yeah. Lab 1, Map Essentials with Miles. That's me. So, leading off, first two things we're gonna talk about is the two types of maps. There's a reference map, it's used for finding physical locations, and it's best for navigation. Then we have thematic maps, used to show specific data, typically colorful and dynamic. You might remember these from page 6 in your manual. We're actually going to look at some of the ones from back then. So, here we have a reference map. Why is it a reference map? It's showing specific data. We've used this for navigation. You can see the school over here. This is where our building would be. This is where our building would be. So it's used for finding things. It's a reference. Here we have another example of a reference. These are streets. Here is a park. Here is a river. More streets, avenues. More streets. It's a lot of streets. So this would be another reference map. Another reference map. Here we have we have all 56. Here we go. So it's referencing the United States. We have our flags over here. This is just the different states. So it's just referencing. Maybe you want to see how close Texas is to Illinois. Not very close. Georgia to Alabama. A little bit closer. We're referencing things. Navigation maybe. Here we have a thematic map. We see dynamic colors. We see it's trying to portray something. Severe, heavy, medium, minor, unknown. Damage done to J2 campus. Here we are again. Here's the campus. This is our thematic map. Let's look at some other thematic maps. Here we go. This says soil moisture. So the different moisture levels of the United States again. We don't have Alaska and Hawaii, but we have continental ones. So continuous, yeah. We have Alabama over here, Georgia, Texas got a lot of different layers going on. California's pretty weird looking. More green over here. Any questions so far?
Nothing so far.
No. Continue. Okay, here's another thematic map. We have percentage of 65 years and older. So this is an age range. It's the theme here. The theme for the thematic map would be the different age ranges in Texas, and this looks by counties. So hopefully no one has a question on that. So we'll be moving on. So scale. What is scale? By the way, we're on page 7, top of it. Scale is defined as the ratio of the actual area to the Earth's surface to map space. So what we see versus what's on the map versus what's actually there. So what we know is actually there. So let's talk about scale a little bit. So there's two types of scale. We have a large scale, which shows a smaller area, has more details. Example here would be a city block. And we have small scale, shows larger area, less details. Example would be a globe of the Earth. The way I like to think about large scale and small scale, if you zoom in on a smaller area, you have a larger scale. If you zoom in on a small scale, you have a larger area, but you lose a lot of detail. If you zoom in on small scale, larger area, less details. Zoom in, large scale, smaller areas, lots of details though. So, any questions on that? Nope. Let's look at some examples of large and small scale. So, these ones should look pretty familiar. They're from your lab manual on page 8. We have large scale and small scale. Small scale is a lot more zoomed out. Large scale is a lot more zoomed in. Other familiar examples is Atlanta, like we talked about, at least in my class. Large scale, small scale. All the details over here are very small, they're very fine. Can't really see a whole lot, but if you zoom in, you get a smaller area, and you get more details, but smaller area. It flips. Look some more. Here we have a very large area, but not a lot of details. We have, we have a smaller area where we have, flip them, more of a state area. We don't see a whole lot of details, but we see a larger area. Versus over here, we see a lot of details, but not a lot of area. It's a zoomed in area of New York City, right here. You can even see in their scales, large and small. So, we'll good on that one. Cool, let's keep going then. So, anatomy of a map. The 6 important things in your map, that is definitely on your midterm. Please take a look on page 9. You have 6 things listed, which is title, symbols, legend or key, scale, compass arrow, or grid. So, let's talk about the first thing, title. It just tells us what we're looking at. That's important to know. Especially if there's a lot going on in a map, you need to know what is this about. In this case, it is Riga, Latvia, Old Town District. So, usually right up top. Continue. Symbols. We have a symbol right here. This one was added in, so it's not in your manual. Don't worry about it. What does this symbol mean? What does this graphic form represent visually to indicate a feature on the map? It represents City Hall. It is a capital area. You might see a bed meaning a hotel, a park bench indicating a rest stop, so on and so on. A school being represented by an apple or chalkboard or stuff like that. Those are going to be your symbols. They just represent things. Maybe the football stadium is a football, or basketball coliseum is a basketball, so on and so on. Those are your symbols. Carry on. Legend or key. This is just going to show us what each symbol or color on the map means. We have water, we have park area, which is green. We have streets, which is this kind of lighter color. We have major roads, which is orange, which you can see through here. It's just showing what each color or symbol on the map represents. And that's our legend or our key. It's interchangeable. So, carry on. Scale. Here's our scale bar. It's just to give the reader an idea of the size and the scope of the given area we're looking at. With a touristy map, you would like to know if you're walking 1 mile, if you're walking 10 miles. Or if you're driving, if one historical site is close to one, or if it's not very close. So that's going to be your scale. Demonstrates the relationship between the map space and the earth space, as we keep saying. Map space to earth space, map space to earth space. So, keep going. So here we have compass arrow, compass rose, north arrow. If you understand that, then you know what it is. Just going to give us an idea of the directional reference. In most cases, it's going to be north arrow pointing to the top. It's just going to be right up in the corner. And that's all really is. That one is just for directional reference. In this case, we have a real fancy compass rose, and we have north. You don't have to label every single one, but north is typically the one you would want to have labeled if you have one labeled. So we have our grid. It's a little bit lighter, but it's also called a graticule. It's just something more overlaid, and we're not going to go super into detail. Just understand that it is important because it's showing how much space and how much area. So continue. So representative fraction. We skip the page. We're now on page 7. We had just gone to page 9, but now we're back on 7. So representative fraction, also called an RF. They're used pretty interchangeably. Most geographers would just say RF though. It's 1 unit of an object placed on the map is equal to X amount of those same units in actual area of the Earth's surface as shown on the map. RF. This could be 1 to 12,000. This one could equal 1 banana is equal to 12,000 bananas on the map. So I want you to understand that it's the same unit in both places. It's typically not bananas, but bananas can be used. So let's talk about how we might read those differently. Oh, go back. How to write a ratio. So, 1 to 17,000 on a scale can be read as 1 in 17,000 miles. No bananas right here. You could also read that as, or a different way of reading ratio could be a scale with 1 in 900 bananas has an equivalent representative fraction, RF, it's a lot easier to say than representative fraction. So 1 in 900 bananas has an RF, the same as 1 in 900. So, simple to read, a lot shorter. You might see it as this. You might see it written out as in 1 in blah, blah, blah units. So, lab 2, still with me. Latitude and longitude, with me. Get into things. What is latitude? Lines of latitude, also called parallels. That is important to know. Please know if they're parallels or not. Oh, do you have any questions?
No.
Oh, cool. Anyways, parallels. These are latitude. These are horizontal lines that measure the degrees of north and the degrees of south on the equator. The equator is at 0 degrees. Let me grab a globe. Equator, 0 degrees. Oh, you're gonna regret holding both of these. Also, by the way, we are now on page 13. Please, if I'm highlighting things, it means I suggest you highlight them. That's how I do things in my class. Set this in. I want to drop it. Too much fault. It's fine. Just leave it. So, talking about the equator. Equator is an important line of latitude because it separates the northern and the southern hemisphere. We live in the good old northern hemisphere. Down here is our southern hemisphere. South, north hemispheres. Oh, I'll put it on this. Cool. So here we have our lines of latitude, like we were talking about. Here's our equator, 0 degrees. Our parallels go up, 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 and down, down, down. 90 degrees. 90 degrees south, 60 degrees south, 30 degrees, you're at our equator, 30 degrees north, 60 degrees north, 90 degrees north. Parallels, latitudes, questions?
Stover Cutfire asked if the midterm is going to be multiple choice, and I replied yes.
It is multiple choice. You guys are absolutely lucky. Cool. I wonder who Stover is. Longitude is the opposite of latitude. Latitude is flat, longitude is long. So you have lines of longitude. These are called meridians. They are vertical lines that measure the degrees of east and west of the prime meridian. So we have our equator. Our equator over here is called the prime meridian, 0 degrees. Unlike latitude, which we talked about, longitude starts at 0 and wraps around the Earth to 180 degrees east or west. So here's our globe again. Now we're going around. Cool. Lines of latitude, longitude. Here's our prime meridian. Put it all right here. Here we see it. So 0, 30, 60, 90. Keep going around. Lines of longitude. These are called good old meridians. Yeah. So let's keep going. As we talked about our hemisphere, oh yeah, we're talking about the hemisphere again. It's still the north, and it's still the south. Oh, let me skip a page. Oh, we skipped 2 pages. There we go. These are our hemispheres. So before I dive into the math, if anyone has a question, please ask it now. I'm about to do math. Any questions that relate to this? Cool. Look around a little bit. So, you have to find your latitude and longitude. A good example of doing this would be our exercises that we did on page 15. They relate to the map on page 17. This map we're about to talk about. It's been blown up a lot, but you can still kind of see the numbers, hopefully. If not, follow along on page 16. So if you want to find our latitude and longitude, for example, let's take Cairo. Cairo is pretty easy to see. So we're going to do, so we're going to go up. Can we see? I'm going to turn this to the So we're gonna go up, up, up. You see 30 degrees north. So we write 30 degrees north. That's our latitude. Now let's go over for our longitude. See, it's a little bit past 30, so perhaps 32. And we know it's east, just like we know this one's north. So we'll put 32 degrees east. So that's how you find your latitude and your longitude. So let me clear this and I'll do another example. Cool. Okay. Let's go over here to good old USA and let's look at New York. So we know New York is right here. So let's go find our latitude first. It's a little bit 30, but below 40. It's not a very straight line, but close enough. So then we can see that this is 41 degrees north. North. That's how we got our north. So let's find our longitude. Let's go over. We see it's about here. Again, I know this might be kind of hard for you to see in person, so just follow along on page 16. So we can approximate, guess, this is about 73 degrees west. West, north, 41 degrees latitude, 71 degrees longitude. Make sure you always have your degrees and your directions. Those are important. Those show us that you know where you're looking, what direction it's in, and that you know the unit, which in this case is degrees. So, okay. It's kind of hard to see. Let's go to Brazil. So let's say you have been given 0 degrees, just 0, and 60 degrees west. This one is 0 because it's on the equator, so you don't need to put which direction it is. It's on the equator. Don't freak out. So if we've been given that, we know it's on the equator, so we know it's going to be somewhere at this right here. And then we know 60 degrees west. So let's go over to 60 degrees west. So what do we see in that area? We see La Paz. Oh, no, wait, no, I messed that up. Ignore that. What do we see that's in right here? Oh, don't erase that. We can see that this is around Brazil. So right now, that was the example for C on the exercise on page 15. So this would be Brazil. Our latitude and longitude that was given, that would be Brazil. So let's keep going. Any questions on finding latitude, longitude, or okay? Cool. So converting latitude and longitude. Give me a second. So how do you know if which formula you're going to be using, if you're going to be dividing, if you're going to be multiplying? So how do you know if you're going to be dividing or multiplying? Decimals and degrees equal division, where if you have minutes and seconds, you're going to multiply. So D in degrees equal division, M minutes, seconds equal multiply. So this is actually from your homework on page 21. We're going to do number 7. Did it skip again? No. Okay, so first things first. Let me get my marker. Okay. Things that are never ever going to change is it's always going to be degrees. Still going to be the same direction that you started in. So let's start with this one. Start this section. So 0.4. ones. Hold up, sorry. The wrong ones. Oh no, we just took them out of order for some reason. Okay, sorry. Make sure I'm doing the right ones. My bad. Okay, let's start this again. Here's what we've been given. So first, let's divide this part, 42, by 6, or 45 divided by 60. So we have 45.5 divided by 60 equals 0.758. We're gonna then, I'm gonna run out of room here. We're going to take what we just got and add on our 42. So here's our 42, that's where we're gonna get that. So 42.758. Now we're gonna divide that by 60. Why are we dividing by 60? There's 60 minutes in a second, 60 seconds in a minute. That's where we get the 60 from. So from there, we get 27.7126 degrees north. That's going to be for our latitude for the first one. Latitude. So what did it change? Degrees didn't change. So degrees. And this didn't change. Our first number. Still the same. And also north. Still north. It's not going to change direction even though we converted it. So let me clear this and we'll work on our longitude. But I'll give you guys a second. Anyone needs to catch up or pause. Now would be the time. And I'm in clear. So next we have our longitude. So same things aren't going to change. Keep that in mind. So first we have our 29.5. 29.5. Divide that by 60. You're going to get 0.32. Sorry. You're going to get 0.49. I'll correct me if you see something wrong. Okay. Okay, so now that we have that, we're going to add this 19 point this 4 1 4. I got a space here. 4 9 1 7. We're going to divide that by 60. We're going to get 32.32 4 9. So our whole answer here is going to be, let's this out, 85 point. This over here. 3 2 4 9. What else did it change? Degrees. And it's still east. Cool. Give you guys a moment for that one. And then we're going to convert the other way around. Any questions? I'll give you guys a moment for that one and then I'll clear it. Okay. So now, this one is the example from your homework on page 21. That was 8. This is now 7. Still in marker mode. There we go. So now we're going to be converting decimal degrees. And so let's do this in blue. So we have our number over here, and we're going to take vary into that. And last time we were dividing by 60, now we're going to be multiplying by 60. So 4.43728 times 60. Here you will get a very long number. 26.237. Okay. So then you're going to take that number, and you're going to take just the decimal, and you're going to multiply that by 60. Getting a little wonky up here, don't worry. Just ignore the 26, focus on the 0.23722 times 60. And from there, we're going to get 14.2332. So from here, we're going to take our 32, 26, and our 14. We're going to get 34 degrees. It's still degrees. 26 minutes. And some of this. 14.23. You don't need to worry about the leftover, just the 23 is good. Second, north. It's still north. Okay? And that's for the latitude. So give you guys a second to do that, and we'll do the longitude.
Alexandria asks, will they need to show work for these types of problems? No, because it's multiple choice,
No,
right?
because it's multiple choice, there's not really a place for you to show work. If you get an answer that's not on your answer choices, then you'll know that you messed up somewhere. Might need to go over and correct that. So no, you won't be showing your work. That's the short answer. But you definitely double check your work if you have something that's nowhere even near one of the multiple choice question answers. So good question. Keep it up, guys. Any other questions? Awesome. Let's clear this, and then we'll work on the longitude. Okay. Here we have next number. As always, you know these not going to change. We know this not going to change. So it's on here. You're going to take the very end of it, just like we did the other one, right up here, so we have a little bit more room. Doesn't get that squish. So 0.713819. And what are we doing if we're not dividing? We're multiplying. So we're going to multiply it times 60. This is converting decimal degrees. So when we multiply that, which was not up there, we are going to get 42.82. So, just like last time, we're going to take just this little bit and we're going to multiply it again. So 0.8214 times 60 again. And then from that one, we're going to get 49.77484. So the way we're going to fully write that out, we're going to take the number that didn't change, very beginning, 119 degrees, still degrees, 42 minutes, and then we're going to have, 42 came from here, 49.74, and then we're going to have, or like I said, 49, oh, we're going to run out of a little room, 7, 5 seconds. I'm just going to rewind it. I'm going to rewind it all the way and pull it out because it got really squished right there. go west. West did not change. Degrees did not change. The first number does not change. Any questions on converting decimal degrees? Nope. Okay, well, I'm pretty sure I'm going to pass the board over to somebody else. Atmosphere. Have fun. Good luck on your midterms.
Hello everyone, my name is Emily. For those of you who are my students, my name is Emily. I'm going to be talking about the atmosphere, and then later I'll come back for lab 6 to talk about atmospheric pressure. So I'm not going to go over the entire lab, just the important things that you need to know, especially for the midterm. So for lab 3, the atmosphere, we're just going to start with the definition of the atmosphere. And so it's the ocean of air which surrounds us from the Earth's surface and stretches all the way up into space. And you can think of the atmosphere like a big ocean. Most of it is concentrated closest to the Earth's surface because gravity is strongest close to the Earth's surface and pulling down on it. And then as you get farther away into space, as you get farther away from the Earth's surface into space, the atmosphere gets less dense, gravity isn't pulling on it as strong. And so there's 5 layers with the atmosphere, and each of these layers are divided by unique temperature characteristics. And the temperature differences are caused by how much energy the layers absorb from the sun. And so the different layers absorb different amounts of energy from the sun, which causes different temperatures. So we're going to start with just going over the layers. So if you look in your lab manual, you have this same exact diagram. If you haven't already filled it in, you can fill it in now as we go over it, or you already did it in class. But the very first layer is the troposphere. And so the troposphere is where we live, and it's where all of the weather happens, because the troposphere has a lot of water vapor. And so of course that water vapor creates clouds and condensation and rain. And so all of the weather happens in this first layer called the troposphere. And so this red line right here is a temperature line. So if you see our axis over here is the height or the altitude off the Earth's surface, and this axis down here is the temperature in that layer. So looking at the troposphere, temperatures range from 20 degrees, and this is in Celsius, so 20 degrees Celsius all the way to negative 55. So it's marking that temperatures go from 20 degrees over here to negative 55. And so that's just showing you temperature and how it changes in the troposphere. And the reason that the temperature drops as you go up in altitude is because the Earth's surface is really warm. It's absorbing all of that heat. And as you get away from the Earth's surface, it's getting colder and colder. So just an important thing to note, I would write down that the troposphere, as you go up in altitude, temperatures are decreasing. So as altitude increases, temperature decreases in the troposphere. That is important. I would write that down. The next layer is the stratosphere. And the stratosphere is important because it has the ozone layer inside of it. And the ozone layer protects us from harmful ultraviolet rays from the sun. So the ozone layer is really important. We're going to talk about it a little bit later. But the stratosphere, this is its temperature line. It ranges from negative 55 degrees Celsius, and it goes up to 0 degrees. And so because of the ozone layer absorbing those sun rays, it's absorbing a lot of heat from the sun, and it makes the temperatures go back up because it's absorbing heat. So that's why the temperature in the stratosphere goes back up. The next layer is the mesosphere, and the temperature actually starts going back down because nothing in the mesosphere is absorbing any heat. So as you go up in altitude, the temperature just keeps decreasing. And so you can see the mesosphere temperature goes from 0 degrees and it goes all the way over to negative 90 degrees Celsius. And then another thing to mention is in between all these layers, there's pauses. And you can think of these pauses as a buffer zone in between each of the layers. And so because they have such unique temperatures in the layers, there's a little buffer zone to give, I guess, space for the temperature to change. And so you have the tropopause, the stratopause, and then you have the mesopause. And then up here you have the thermosphere. So the thermosphere is pretty big. It's one of the biggest layers. And the temperatures go up really high in the thermosphere because it's getting closer and closer to the sun. And it's also absorbing a lot of heat too. So inside of the thermosphere, you have auroras, which is just like the northern lights that you see in maybe movies or maybe you've seen in person. But the auroras are just the northern lights. And then the ionosphere is made up of charged particles, which are called ions, which is why it's called the ionosphere. And these charged particles are actually what makes long distance radio communication possible. And so people will send up sound waves or radio waves up into the atmosphere, and they hit these charged particles in the ionosphere, and those radio waves come back down to Earth to go wherever they were meant to be sent. So that's a fun fact about the ionosphere. And then the last layer is the exosphere, but before the exosphere, there's a little thermopause for that buffer zone for the temperature to change. And the only thing you need to know about the exosphere is that it's the very last layer, and this is where basically the atmosphere thins out into space. And this is where gas molecules or any atoms, if they floated all the way up there somehow, they can just be lost and drift into space and never be seen again. So all you need to know is exosphere. Exo is the outside, so it is the outside layer of the atmosphere. Okay, so those are all of our layers, and this is our temperature line showing the different temperatures throughout those layers. Any questions? Okay, so now we're going to talk about the ozone. Ozone's super important, like I said, because it protects all biological life from these harmful ultraviolet sun rays. And without the ozone layer absorbing those sun rays, if they were to make it through to the Earth's surface, those sun rays are so powerful that they could kill our vegetation, our crops that we eat. It could cause skin cancer, or even the sun rays will kill the plankton in the ocean, and the plankton is what creates all the oxygen that we breathe. So that's really important. So we want to make sure that we keep our ozone layer and we don't lose it. But something is happening that's kind of hurt it or created the hole in the ozone layer. And what that is that humans are just releasing chlorofluorocarbons, or otherwise known as CFCs, chlorofluorocarbons. And so these CFCs just hurt the ozone layer, and they basically just destroy ozone, creating a big hole, which let those sun rays through, which is what we don't want. So ozone can be really helpful if it's in the stratosphere, in the ozone layer where it's supposed to be. But if it comes down into the troposphere, it can be seen as an air pollutant because it's really bad for you to breathe, because ozone itself is very unstable. We breathe in O2 molecules, but ozone is a O3 molecule, and oxygen itself likes to be paired with a partner. So that's why O2 is stable, that's why we breathe it, because the oxygen is paired together with a partner and it's happy. But if you have ozone, which is an O3 molecule, there's one little oxygen that's by itself. It doesn't like that. So the ozone layer is constantly breaking apart and reforming, but even though it's breaking apart and reforming, it's staying at an equilibrium. But again, humans are interfering with this equilibrium by releasing these chlorofluorocarbons. So we need to make sure we keep our equilibrium. And then the last thing we're going to talk about is the air quality index. And so, like I said, ozone can be an air pollutant. So that's why we have the air quality index to basically measure the level of ozone and also other air pollutants in the atmosphere. And this is what the air quality index looks like. It has different ranges. And so if the air quality is anywhere between 0 and 50, that means you're good. Everything's healthy, you're fine. But if you get to yellow, it's kind of moderate. It's acceptable, but it could be a risk for some people who might have other issues. But then once you get to orange, this is when an ozone alert is issued. And so anybody that might have prior conditions or anything, they might need to stay inside or get some oxygen. So if it's orange, an ozone alert is listed, and then anything else is just really unhealthy. But if you look right now along the West Coast, because of all those wildfires, their air is in these ranges, the very unhealthy ranges. So a lot of people are having to stay inside or use oxygen masks. So I say if you get to Maru, which is hazardous, anything above 300 is really, really bad. So this is just the air quality index. Any questions? No? Okay. So that's all I have for the atmosphere. I will be back for lab 6. I'm gonna hand it over to Dexter now to talk about Earth-Sun relationships.
I'll read the questions, Dexter.
All right, my name is Dexter. You guys in my class know me. If you're not in my class, you obviously don't. But I'm a graduate teaching assistant here at JSU, just like Miles and Emily. So we're going to be going over Lab 4 and Lab 5, which are extremely similar. So first off, we are going to be talking about the perihelion and the aphelion. So the things you need to know about them: the perihelion is the point in which the Earth is closest to the Sun, and it is 91.5 million miles away. And next thing you need to know is the aphelion, and that is the point in which the Earth is farthest from the Sun, and it is a 94.5 million miles away. All right, so as we learned from Lab 4, the Earth's maximum axial tilt is 23.5 degrees. And what it is called when the Earth's tilted at its maximum is a solstice. And we have two different types of solstices. The first one is the summer solstice. It is on June 21st. And that is the day the most sunlight reaches the northern hemisphere. And inversely, that is the day the least amount of sunlight reaches the southern hemisphere. The winter solstice is on December 21st, and it is the opposite of the summer solstice because that is the day the least amount of sun reaches the northern hemisphere, and the day the most amount of sun reaches the southern hemisphere. Do we have any questions on the helions and the solstices?
No, no questions.
Got it. All right. Next, we're going to be covering equinoxes. And equinox is when the Earth is tilted at 0 degrees. And that means that all of the Earth that is facing the sun receives equal amounts of sunlight. So first we have the vernal equinox, which is on March 21st. And then we have the autumnal equinox, which is on September 21st. All right, so in Lab 4, we also cover the tropics and the circles. So what are the tropics and the circles? The tropics are lines of latitude that mark the furthest extent that the Earth receives direct sunlight. So we have the Tropic of Cancer. So at around 23.5 degrees north, that is when the Earth receives that's the furthest extent the Earth receives a direct amount of sunlight. And same for Tropic of Capricorn, which is inversely 23.5 degrees south. So 23.5 degrees north is the place where the Earth receives the last amount of direct sunlight, and so is 23.5 degrees south. So inversely, the circles are lines of latitude which mark areas that may receive no sunlight during certain times of the year. Places in the circles or past the circles sometimes go days without sunlight. Sometimes they have entire days that are just pitch black. So we have the Arctic Circle, which is 66.5 degrees north, And then we have the Antarctic Circle, which is 66.5 degrees south. All right, for lab 5, we're going to be talking about declination. So the definition of declination is the angle at which the Earth receives light from the sun. Easy peasy. So before we get into higher and lower declinations, we need to get into positive and negative declinations. So if you look on your analemma, which is on page 40, you will see that on the left side and on the right side, it has marked where the equator is, where the Tropic of Cancer is, and where the Tropic of Capricorn is. So essentially, anything above the equator on the analemma, it has a positive declination, and anything below the equator has a negative declination. And we'll get into more on that later. So in whichever area you're looking at the declination, a higher declination means that there is more direct sunlight, and that means there is more daylight. So that means if you're in the northern hemisphere and it has a positive declination, then that is more sunlight. And lower declinations mean less direct sunlight, and that means less daylight. So if you're in the northern hemisphere and you have a negative declination, that is also less daylight. All right, so finding the declination is pretty simple. You look on your analemma, and the declination is going to be your y-axis, and the time of the year is going to be your kind of x-axis sometimes. So essentially, let's find the declination of September 15th. On your analemma, you'll see September marked on your graph, and you'll just follow the line, and September 15th will have a declination of 4 degrees. If we want to find January 15th, that would be a declination of 22 degrees. All right, so solar angle is if the sun is giving direct light. We went over a positive and negative, so we're going to figure out how to calculate solar angle. So the equation for dates that have a positive declination, so that is anything above the equator on your analemma. It is solar angle equals 90 degrees minus the absolute value of the latitude plus declination. So essentially, you're going to do this in here first, latitude plus declination, and it should be positive unless you're working in the southern hemisphere. But you'll get the absolute value of that, and then you'll subtract it by 90. And this is also in your book on page 41. And then we have the equation of dates with a negative declination, which is the adverse of that. All right, so first we'll talk about what is the solar angle of Jacksonville on November 15th. So if we look at our analemma, we will see that because we are in Jacksonville, 33 degrees north, and our declination is in the southern hemisphere in November. November 15th is about a 19 on the analemma. So what we'll do is the solar angle is equal to 90 minus the absolute value of 33 minus 19. So that would be 14, and then it would be 90 minus 14, which would be 76. And so the solar angle of Jacksonville, Alabama on November 15th would be 76 degrees. So then we'll go over an example of a positive declination. So what is the solar angle of Jacksonville on April 25th? So as we see, April is above the equator, and April 25th is around the 13 mark. So we'll take 33 plus 13, so that would be 46. And then we have 90 minus 46, which is 44. And then we'll have a solar angle of 44 degrees. Do we have any questions on any of the declination stuff?
Nope.
All right. And next is Emily again with atmospheric pressure.
Okay, so now we're talking about atmospheric pressure, just going over some basics, not everything in the lab, just what you need for the midterm. Okay, so like we just said for lab 3, the atmosphere is the ocean of air, and this ocean of air is held to the Earth's surface by gravity. And the weight, the pull from gravity, that weight caused by gravity is what's known as atmospheric pressure. And so pressure is strongest closest to the Earth's surface and then decreases as you increase in altitude. So remember, as we go up in altitude, gravity is getting weaker, our pressure is weaker, there's less gas molecules. But if you're close on the Earth's surface, gravity is strongest, the atmosphere is the densest there, that's where all your gas molecules are concentrated. So this is important, I would make a note of this. And then another thing is to measure pressure is a barometer. You use that instrument to measure pressure. So make sure you know that a barometer measures pressure. Okay, so you have this diagram in your lab manual. If you haven't filled it out, you can fill it out now. But all of this is showing us isobars. And what isobars are is they just map out pressure for you. And so how isobars work is that it is a line that joins points of equal atmospheric pressure. So if you look at this line for an example, this is 1,008 millibars, and millibars is the unit that we use for pressure. It's usually just written as MB. So 1,008 MB or millibars. Anywhere on this line is going to be 1,008. So over here in Texas, that's 1,008. All the way over here through Tennessee, going up all the East Coast, is all going to be 1,008 millibars. And then say maybe this line right here, 1,016, everything touching this line is going to be 1,016 for the air pressure. So now that we know how the isobars work, then it shows us where our areas of high pressure and low pressure are. So right up here is going to be our area of high pressure because this is where pressure is the greatest. So if you want, you can write high pressure. And then down here is going to be our low pressure because this is where the pressure is the lowest, it's at 1,000, and then it's at 1,024 up here. And so biggest thing to remember is that the wind blows from high to low. So looking at this map, our high pressure is here, our low pressure is here. So we know that the wind direction is going to blow downward across the US in this direction, going downward. So air always blows from high to low. And then another thing is that the isobars can make what's called troughs or ridges. So if you see, pretend these black lines are isobars, and if you see them, a bunch of isobars, like in this case it's 3 of them, start sloping down into this U shape, that's called a trough. And then if they start going up into this hill shape, this is called a ridge. And so looking back at our diagram in the manual, we have our high pressure, we have our low pressure, our wind is blowing down this way, and then right here in the middle is a nice trough. So you can see it's a trough because it's all kind of going downward in a U shape. Okay, so our pressure gradient, we talked about there's 3 factors that influence the air movement, and pressure gradient is one of them. And all you need to know about pressure gradient is that the wind blows from high to low areas. And then the next factor for air movement is the Coriolis effect. And so all the Coriolis effect is that it spins, is how the air spins and how it goes up and down. So the pressure gradient is how the wind blows horizontally across from high to low, but think of the Coriolis as our up and down air movement. And so what this is showing right here is different pressure cells, and these circles are our isobars. Even though they're perfect circles, and in nature it's not going to be a circle, but for this it is. And the isobars also aren't labeled, but it has an H and an L to show you that this one has high pressure and the pressure is getting lower as it goes out. And this one has low pressure in the middle and the higher areas are on the outside. So if we're talking about pressure gradient, it's gonna go from high to low. But if you also add in the Coriolis effect, it's gonna make it spin. So depending on what hemisphere you're in, depends on what direction you spin. And this is because of the Earth's rotation. So the Earth is rotating and the different hemispheres the wind is spinning different directions. So we have our equator right here in the middle, and this is our northern hemisphere. Here's our southern hemisphere, and this is just showing you what the different cyclones and anticyclones do. So our high pressure areas are always going to be anticyclones. So this is an anticyclone, this is an anticyclone, and then these two are just cyclones. Anything with low pressure is a cyclone. So if you want to circle that, if you haven't already, these are our anticyclones, are always going to be high pressure, low pressure is a cyclone. So looking closer at these arrows, you can see that they're pointing from high away down to low. And then same with this one, it's pointing from high areas into the low. So it already has the pressure gradient pointing from high to low, and then it also has the Coriolis effect spinning. And so based on the hemisphere, say if we are in the northern hemisphere, then our anticyclones circulate clockwise. So everyone knows that this is clockwise, right? Because we can all read clocks. And so this one is counterclockwise. And then in the southern hemisphere, it's just the opposite. This one is clockwise, while this anticyclone is counterclockwise. And so this is just showing you the pressure gradient and the Coriolis effect together. Also with the third force of friction, because friction, all that does is just slow down or minimize the other two effects. So friction just slows down the pressure gradient and it slows down the Coriolis effect. I think that's it. So any questions, dude? Okay. So that's everything for Lab 6 that could possibly be on your midterm. It is multiple choice, so you won't have to draw any arrows like you did for the assignment. But this is it for Lab 6, and that's it for the entire midterm study review. If there's any questions, you can ask. This is recorded, so people will watch it later. And then if you have any questions over the weekend, you can always email any of us. Email me, Emily, Dexter, or Miles. We'll respond. So I think that's it. Thank you so much for coming. Hope you do good on your midterm.